how much time is left, but we'll see.
Our last speaker for this conference is Saad Mneimneh,
Yes.
and he will speak on affiliation networks and with preferential attachment and subsumption.
Yes.
Take it away, Saad.
Thank you. Thank you for the invitation. This is work I did with my PhD student a few years ago. And let me tell you a little bit about the motivation for the work, and which will also highlight the setting. So our motivation was network growth with preferential attachment, especially in social networks where nodes that are highly connected are more likely to acquire new neighbors. And this idea of preferential attachments in graphs was, I think, became popular in the 90s. But the idea itself existed before in different settings and with different names. One feature that we get from preferential attachments in graphs is the power law for the degree distribution. And what this means is that if you look at the probability of a degree k, is going to decrease as a power of k. So we can write something like P of k is 1 over k to some power, something like that. So that's the power law. Maybe I can write it down. Yeah. So pk is proportional to something that is decreasing in k to some power. So we were looking at some networks, and they did not exhibit this power law. So we were, skeptical about why that's not happening. And one suggestion is that they're not grown preferentially, and another suggestion was that maybe there is some kind of a power law hidden somewhere if we can view them differently. So that was kind of like the motivation for doing this. And it turns out if we view these graphs as hypergraphs or some other kind of hypergraphs like simplicial complexes, then a power law does emerge. So we started basically doing that. And one idea associated with this is that if that's true, then what is the preferential attachment mechanism underlying these networks at the level of the hypergraph or the simplicial complex? So let me tell you about affiliation networks to start with, and how we can view them as hypergraphs or in other ways. So what's an affiliation network? It consists of a set of nodes and a set of affiliations with a relation between the two. And so on the right side, you can see it's essentially a bipartite graph where we associate nodes with affiliations. Here, it's like a scientific collaboration network. It's a very small one where nodes are people and affiliations are the papers they wrote. And if every paper had exactly two authors, then we could represent this as a graph with an edge between the two authors. But more naturally, we can view this network as a hypergraph where each paper becomes a hyperedge. So that's on the left side somehow. So there's nothing fancy here. So this is basically the first way, or the one way to model these affiliation networks is by using hypergraphs, and each affiliation here is an hyperedge. Basically, that's one way to do it. Another idea was to use simplicial complexes, and I have to say here, like really, what I'm using of the simplicial complex is something very simple. So I'm not really using the simplicial complex fully, but the idea is, in the abstract simplicial complex is simply a collection of sets, And it has an interesting inclusion property that if F is part of the collection, then every subset of F is also part of the collection. That's the idea, and we call these subsets faces, and the maximal subsets are the facets of the simplicial complex. So I'm showing an example here. 1 to 3. I mean, does it show nicely on the screen? Yeah. Okay. So 1 to 3 is a set, and so every subset of that is also a set. It's included, and so we may just look at the maximal ones. Any simplicial complex is nicely represented by its facets, and so in this case, I have something like a triangle if I want to be geometric, right? Something like a triangle and an edge. Basically, that's it. And implicitly, I understand everything that is a subset of the triangle is there as well. But I'm going to say that the affiliation in this model is the facet. And this is where subsumption, which is like deletion of affiliations, implicitly occurs. If at any point in time an affiliation becomes part of another, it goes away. Even though my understanding is that all of them are there, well, actually, it doesn't matter. If none of them is there or all of them are there, it's the same. It's just a perspective. What I care about is an affiliation is just a facet. And so that's the distinction between the two models. It's a little bit counterintuitive because on one hand, I'm saying all of the subsets are there, and on the other hand, I'm saying no affiliation can be part of another, but this is just a perspective. Okay, I hope it's not confusing. I mean, I thought about it several times. So maybe another way of saying it is to say we have hypergraph, right, is one way, and another way is a hypergraph with no inclusions. So that's one way, another way of saying it. And so these are the two models I will consider. So hypergraphs, I will define the degree of a node as the number of hyperedges it belongs to. And with simplicial complexes, where affiliations can be subsumed as soon as they become part of others, I will define the degree of a node as the number of facets that it belongs to. And this is the distinction between the two models. And so let's look at some example graphs and how they look like in terms of their degree distribution. On the left, in green, that's a random graph. And if we look at the degree distribution, it's a Poisson, or it reaches a Poisson at the limit. And on the right side, we have a network that has been grown by preferential attachment, where, again, nodes with high degree are more likely to get new neighbors. And the degree distribution here is a power law. And one useful way, or typically how people look at these, is by looking at the degree distribution in a log-log scale, because power law looks like a line. Essentially, that's how you identify it visually, although it can be tricky. So this is what I'm showing in the last plot, where the degree distribution of the preferential attachment network looks like a line in the log-log scale, whereas the other one doesn't. Okay, so some examples that we can look at is this a power law? Well, it's not a line. So it's not, but you might say, well, asymptotically it is somehow. So for high degrees, it looks like a line, so that could be a power law. Fine. How was this network obtained? It's basically a bigger network of authors and their papers. So the nodes here are authors, and there's an edge between two nodes if they co-authored a paper. And so if we look at this, we're doubtful. Doesn't look like it has the power law. But if we replace the graph with a hypergraph instead, where each paper becomes a hyperedge, and we, of course, plot the degree distribution based on the definition of the degree being the number of hyperedges you're in, then it is more obvious this is a power law. This is another example taken from a Facebook friendship graph. The usual here, people are the nodes, and there's an edge between two if they are friends. And when we look at the graph level, we don't see a power law. But if I replace this by a simplicial complex that is based on maximal cliques, okay? So the facets become the maximal cliques, and then with the redefinition of the degree, I actually do observe a better behavior in terms of the power law. So this suggests that there is some kind of growth in the network that is preferential, but not at the level of the graph, at some other level.
So when you say at the level of the graph in a co-author graph, all the people who have written a paper with each other are connected.
Yes.
And
So the graph is pairwise, obviously.
Mm-hmm.
Every two nodes are connected by an edge if they are co-authors.
And the affiliation graph is where it's like a bipartite graph.
Yes. The affiliation is all people who have co-authored some paper. If they make a clique, then that becomes the affiliation, a maximal clique. I mean, of course, every clique has sub-cliques.
So it's not a bipartite one, it's the maximum.
Hypergraph.
Right.
Yes, but it's a bipartite with no inclusions. But yes, forget about the bipartite. It might be confusing. It's a so by construction, when you take maximal cliques, right, it is a simplicial complex because every maximal clique includes all the cliques in it as well. So is that clear to everyone? So the first example shows the hyperedge model, and the second example shows the simplicial complex model. Well, in both cases, the idea is that it's a more distinctive, it's a better indication that there's a power law. Okay, so we're not the first to actually study preferential attachment in affiliation networks. We had some work in the literature. I'll just go quickly and highlight what we thought was not, nice enough, right? So in the first work, they considered preferential attachment in hypergraphs, but that led to a very symmetric degree distribution in terms of the degrees as well as the size of the edges, which was a little weird. I mean, not general enough. It was very specific in that way. It also, of course, does not have any subsumption as part of it because it's based on hypergraphs. The second one studied preferential attachment in simplicial complexes where there is subsumption. Their goal was to match a given facet size distribution. That was given as an input. Two drawbacks. One is they had to select nodes explicitly based on their degree. So their choice in growing the network explicitly has to go through nodes and select them based on their degree, which we thought is not very natural. And the second thing is that subsumption dies out when the network grows. As the number of facets go to infinity, you have no more subsumption. It dies out. So it becomes like a hypergraph, really. A hypergraph, yes. And the last two, I'll just go quickly over them. They were also very specific in that they were growing in simplicial complexes, only triangles and edges. So it did not provide a general enough framework to study networks in general. And so we wanted something like this, a preferential attachment model for affiliation networks that is realistic in some way, right? Simple enough to be studied, rich enough to exhibit interesting properties, and could be the basis of how networks actually grow. So we want power law in the degrees. We want implicit preferential attachments. We don't want to sample nodes based on their degree explicitly. So I will talk about that. We had also something like a locality parameter. Somehow affiliations were created by sampling a few number or a small number of existing affiliations. So that's like a locality parameter. And of course, subsumption doesn't die out. It has a probability that doesn't go to zero. So we wanted all of these conditions. So here's our model. I mean, it's not very surprising. We have three parameters. Alpha is a number between 0 and 1. C and L are two positive integers. And so here's what we do. We sample L hyperedges or facets, depending on the model. So we sample L affiliations uniformly at random. And then we look at all the nodes in these affiliations. We can either construct this by a union or by a multiset. Either way, it doesn't change too much. We will look at that. And once we have the nodes, we pick each one independently with probability alpha over L. And then we add C new nodes that did not exist in the network, and we make a new affiliation out of the sampled nodes and the new ones, and we add it to the network. And if we are in simplicial complex, we check, is this affiliation subsuming any existing ones? If that's the case, we delete them. In hypergraphs, that's okay, we don't care. So this is our general algorithm for growing networks. And at the time we thought, okay, this seems to be realistic, right? Consider the example of papers. How do we add more papers? I mean, we must have read some papers, and then we identified some authors in those papers that we thought maybe we can collaborate with. We collaborated with them, and we created a new paper, and we added ourselves to the network, right? So that's kind of like a realistic model to think of. But of course, we have to analyze stuff. Okay. So where does preferential attachment come from? Intuitively, I mean, don't look at the formulas yet. Maybe, I mean, they're not that. One aspect is important, but so I will go over that. But intuitively, a node that is part of many affiliations is more likely to be picked. That's where preferential attachment happens. So what is the probability that a node will gain a degree? Well, I have to sample its facet, its edge. I mean, we're talking hypergraphs here. So I have to sample its edge, and then I have to pick it, right? So what's the probability that I will sample some of its edges? It has k edges. So the probability that I sample none is 1 minus k over m, where m is the total number of edges. So 1 minus k over m to the power L, because I sample L of them. So that's the probability of not sampling any. And 1 minus that is the probability that I sample some. And then after this, alpha over L is the probability that I pick the node. So that's the expression with the union variant. With the multiset, it's slightly different. Doesn't matter. What's important is that asymptotically, or when k over m is small, both of them are approximately alpha k over m. And so if that's the probability of gaining a degree, it is proportional to k, which is the current degree. So alpha over m here is the proportionality constant. So these two variants I mentioned, because they're not really relevant unless you are talking about a small network. When the network grows, if we believe that k over m goes to 0, then they are both similar. That's the idea. For small networks, they're interesting on their own, but I'm not going to discuss that. Now, the idea that k over m goes to 0 is reasonable, hard to check, because how do I know this is happening? I want to make sure that all degrees are small enough compared to the network size. We had an alternative condition, which is the probability of sampling overlapping edges goes to 0. So when we sample these L edges, the probability that some of them overlap goes to 0. And that implies that k over m goes to 0 anyway. So we observed this experimentally, it is true, but we also proved it based, given some conditions, and I'm not going to go over that. But the assumption is, which we call the no overlap assumption, is that when we sample facets, they don't overlap. So that's preferential attachment. Why does that imply power law? I'm going to briefly discuss how this happens. This is not like genuinely new. Typically, what people do is they track nodes with degree k and check what's happening. So let nt be the number of nodes at time t. That's just c times t because we add c nodes every time. ntk is the number of nodes at time t with degree k. That's what we're interested in. And m sub t is just the number of edges, which is just t because we add one every iteration. And so now we want to track the expected number of nodes with degree k. So at time t plus 1, okay, the expected number of nodes with degree k is equal to what? That number at times k, at time t, right? Minus what we lose, any node that had degree k and gained a degree, and so now has k degree k plus 1, so we lose those. And that happens with probability alpha k over t, plus the nodes that we gained. So every node that had degree k minus 1 gain a degree and now have degree k. And that happens with probability alpha k minus 1 over t. That's the preferential attachment property. Plus, if k is exactly 1, we actually do gain c more nodes. Those are the ones that we just added. And they have degree 1 because they belong to only that edge. So this is somehow the equation. And then all I need to do is replace expectations with probabilities. Yes?
I'm not sure if I'm only missed the model. I thought you had edge, you just added more edges, but you're saying you modify existing edges in this process. Is that right?
No. I sample some edges,
Right?
right? Extract nodes from them with probability alpha k or whatever, and then add new nodes and make a new edge.
But in this process, you're building a hypergraph. You keep the edges from the previous times that you added.
Yes, I keep
those
them.
aren't changing. And this whole process, this is describing the process of building up this new edge.
Yes, this describes in building this new edge. This is how the number of nodes with degree k will change. Some nodes will gain a degree, and some won't, right? And when a node gains a degree, it will either the ones that I'm interested in are those that will go from k to k plus 1. So I will lose them as having degree k. And those that go from k minus 1 to k, so I will gain them as having k. So I'm tracking that change to see what can I say about the number of nodes that have degree k, how they change from time to time.
May I ask an elementary question?
Yes, go ahead.
When you talk about the degree of a hyper edge, it is the number of connections, number of other hyper edges it is attached to.
Yes.
Including all the nodes in those hyper edges.
No. So now we define the degree of a node as the number of hyper edges it belongs to.
Number of hyper
Only. The hyper edge could contain many nodes or not, it doesn't matter. So it's not pairwise anymore. That's the thing.
Yeah.
So with the graph, you look at all your neighbors.
Yeah.
Here, we're only looking at how many hyper edges I'm part of. Like if I'm an author, my degree is how many papers. Even if a paper has 1,000 co-authors, it doesn't matter. It's just one. Yeah. And so this tracks how degrees are changing over time from t to t plus 1. And
what's the C? Yes, those make sense as to that you're subtracting and adding. That C is just the
C is the number of new nodes that you add. So they're only relevant if k is 1, right? If I'm looking at how many nodes of degree 1 do I have, then I just gain C of them, right? That's only interesting if k is 1. In general, it's not. So if k is equal to 1, we just gain C. Otherwise, no. Yes. But I mean, it doesn't matter if k is large. That's irrelevant, actually. But anyway, so now if we replace expectation with probability, the number of nodes at time t that have degree k is simply the number of nodes at time t times the probability of k. And I'm going to assume that this probability of k at time t converges to just pk, right? It doesn't matter if it's at time t or t plus 1. So when I replace expectation by these probabilities, c goes away and t becomes irrelevant, and I get a recurrence. Okay, so we don't have to look at exactly how this happened. We get a recurrence in pk in terms of itself and pk minus 1. That's the idea, that now we have a recurrence, and if we work out this recurrence exactly, we can actually solve it. And so pk turns out to be this expression where I have the gamma function. And using what I know about the asymptotics of the gamma function, like Stirling approximation, for instance, I can easily conclude that this is a power in k, and the power is minus 1 plus 1 over alpha. So my gamma, which is in the power law, is 1 plus 1 over alpha. And that's a known distribution, by the way. It's called the Yule-Simon distribution. And one interesting observation is it doesn't depend on C or L, only on alpha. So that's kind of like a nice thing. These are just examples where we actually simulate, and obviously the blue dots are actually obtained from the simulation. So these are, each dot represents a number of nodes with that particular degree. And then there's a blue line, which may not be very obvious. That's the actual expression that I showed you before. And then there's the dashed line. This is just the slope, k to the power minus 1 plus 1 over alpha, just to show that they align well. So this is showing that we do indeed obtain a power law from this kind of procedure. Okay. What about the edge size? Okay, so I'm going to try to quickly describe how this happens. So here now I'm interested. I'm done with the degree. Now I'm interested in the distribution of the edge size. And so how can I create an edge with size S? Well, first I have to sample L edges. Each one will have some size Si with probability PSI. And then I will have to get all the nodes from these edges. And with the no overlap assumption, this number is simply the sum of the S's, because they don't overlap. So the total number of nodes is just their sum. I have to select exactly S minus C of these, so that some of the S's choose S minus C ways, right? Because I'm adding C later. So to make S, I need to choose S minus C. Each such node has probability alpha over L of being chosen. So that's alpha over L to the power S minus C times 1 minus alpha over L to the, the sum minus that. This is just the binomial probability, essentially. Okay. And that's a recurrence for P of S, sum over all S's, of course. So that's how I can form an edge of size S. What can I do with this? It's not a nice recurrence. So what we did is we transformed into its generating function, multiply by x to the power S on both sides, and sum over all S's, we get something nice. And so I multiplied by x to the power S, sum over S. I did the same thing on the other side. I actually split it into x to the power C and x to the power S minus C, so I can combine it with this. And if you see the sum over S and the last three terms, that's just the binomial theorem. So I can replace it with this expression here, 1 minus alpha over L plus alpha over x to the power sum of the S's. And then it's not hard to see that the sum can be obtained by multiplying the sum on the next line by itself L times. It's not hard, but what this means is that this inner sum is, by definition, is the generating function at 1 minus alpha over L plus alpha over L x, and multiplying that by itself at times is just to the power n. So basically, I obtain a recurrence for the generating function. So f of x is x to the power c times f to the power l of at some other value. It turns out, it's nicer to work with this because PS is too complicated. We can derive certain things, certain properties from f of x. So in the special case when L is 1, if we iterate this recurrence, we find that f of x is the Pochhammer symbol, was like something known, whatever that is. We can find the expected size of the hyperedge by finding the derivative at 1. That is also known. And we get c divided by 1 minus alpha, which is not surprising because we could have derived it in other ways. And by using something like the handshake lemma, where like the sum of all degrees is equal to the sum of all hyperedge sizes. And then we can relate the sum of degrees to sum of hyperedge sizes, and we get the expectation of the degree is the expectation of S divided by C, so we get 1 divided by 1 minus alpha. So all of that we can get from this generating function. Okay. Now, what happens if we move to simplicial complexes? So I will highlight the complications and how we can address them and why we still get similar results. So we have the no overlap assumption that when you sample facets now, they're not hyperedge, when you sample facets, they don't overlap. We add another assumption that there is no accidental subsumption. What does that mean? The probability of subsuming a facet different from the L sampled ones goes to 0. So it means like when you sample the L facets and you pick nodes from them and you make a new facet, there is a chance that you will eat up one of them or more, right? But no other facet will be affected. Of course, that's not true, but the assumption is that the probability of this happening goes to 0. And we verified this experimentally. We also proved it under certain conditions. We're not going to go into that. But this means that I can retrieve this idea that a node will either gain a degree or not. It won't lose because I won't be able to subsume facets that are not among these L ones. So this is the idea. So I basically retrieve the setting where a node will either increase its degree by 1 or not. That's the main issue, or that's the main idea. But now I have to consider what is the probability of gaining a degree. Before it was alpha k over m. Okay, but now I have to make sure that the facet is not subsumed, because if it is, then I lose one and I gain one, and then nothing happens. So it's alpha k over m times the probability that I don't subsume the facet. Well, what's the probability that I don't subsume the facet? Well, the probability that I subsume the facet is the probability that I take all other nodes in it. So that's alpha over L to the power S minus 1 times the probability of S sum over all S. But this probability of S is conditioned on the fact that I have a node of degree k in the facet, which I cannot ignore, unfortunately. So that's another complication. So, for instance, if I tell you that a facet has size C, what is C? C is the number of new nodes that I add. So if a facet has size C, it means it's completely detached from anything else. This means these are C new nodes that I added, and every node has degree 1. So there is dependence between degree and size. I cannot ignore. And so this is the complication. I can get rid of it. So I have two things that I need to worry about. One, the probability of adding a degree has changed to something that looks like too complicated to deal with. The other thing is n, the total number of facets, is not known anymore. because some of them are lost over time. Before, in the in the hypergraph case, I knew it was exactly t, because I add one each time. Now I don't know, so some may disappear. So this becomes some kind of a random variable, which I need to also address. So let me tell you how we got rid of the complication that PS depends on K. Well, we simply said we only care about when K is large. And when K is large, PS conditioned on K converges to something I will call QS. And so what does it really mean? So Q of S becomes the facet size distribution among facets that contain a node that have a very high degree. We call these mega nodes. And we hope that, okay, this is something that we can find in the network, right? So this is something that exists, this idea of the facet size distribution when a node has a very high degree in the facet. So we call this Q of S, and this way we cancel the dependence on K by actually making K go to infinity. And if we do that, and we repeat what we did for the facets for facet size distribution, find the generating function, facet size distribution among facets with meganodes, find the generating function. If we do that, we can retrieve a recurrence that is very similar to the one we had before, except that our alpha is multiplied by an extra factor. And that factor has H and F, which represent the generating functions that I just mentioned. So f of x is simply the generating function of the facet size distribution. H of x is the generating function of the facet size distribution when you have a meganode. And assuming we know them, we can find this factor. So alpha becomes alpha star, which is slightly different than alpha. But we can compute it if we know how to find these things. So that's the idea. How do we find them? Well, okay, we have some complicated recurrences for them. Not important because we don't know how to deal with them. The way we dealt with them is by figuring out how to solve them numerically. And we developed some methods to figure them out, which I'm not going to discuss. But that's if we really want to find alpha star, then yeah, we can actually do that computationally. Some properties that are interesting. In hypergraphs, I mean, we can also study the facet size distribution when facets have a meganode. In hypergraphs, we didn't need to, but we could. So in hypergraphs, it turns out h of x, which is the generating function corresponding to size distribution with meganodes, turns out to be x times f of x. And so this corresponds to, in probability, this means that we have a shift. So Q of S is simply P of S minus 1. And in simplicial complexes, this is also true, but only when L is equal to 1, which also implies that alpha star is alpha when L is equal to 1. So if we were sticking to L equal 1, we didn't have to worry too much. This particular expression, f of alpha over L, has a meaning. If we use the definition of the generating function, it's the sum of alpha over L to the power S times P of S. That's just the probability of subsuming the entire facet. So this is somehow the probability of subsumption. Yes?
I'm just confirming, L is the number of facets you sample.
Yes, yes, correct. And so f of alpha over L is the probability that we subsume a facet. And that doesn't necessarily go to 0. So we're happy that there, it is some number, whatever that is. This is just showing experimentally what's happening. So we know L times f alpha over L is now the expected number of facets you subsume per iteration. And so we're plotting that experimentally for some examples for different C's and L's as a function of alpha. What we see is that when L is 1, the probability of subsumption or the expected number of subsumptions grows with alpha. And when L is not 1, in these examples, I have L equals to 2, the fraction of subsumed facets somehow goes up and then comes down again, and possibly going to 0 as alpha goes to 1. And I think the reason for this, I'm not really connected to it as I was before a few years ago, but I think one reason for this is the following. The probability of picking nodes is alpha over L. When L is 2, the best you can do is half. So the probability of picking nodes is at most half. But when alpha grows, the size of facets grows, but the probability of picking nodes is capped at half, so it becomes harder to absorb them. And that's not the case when L is equal to 1, because then alpha over L can go to 1. I think that's the reason why we see the drop. On the other figure, we have alpha star over alpha, just showing how alpha star and alpha behave. I mean, they're the same when L is equal to 1. That's the bottom line. But they are not the same when L is not 1. Okay. And here are some examples where we actually simulate with different values of L and C. For a given alpha, here alpha was fixed at 0.5. We change C and L, and we compute the gamma, the power, which is 1 plus 1 over alpha star. And the tables show, one of the tables is what we found experimentally by fitting. That's the top table. And the other one is what we get by actually computing gamma from alpha star using the generating functions that I showed before. And we see there is some, it's consistent. There's the computation versus the experimental. Now we have, so this will be my last slide. I want to mention that we have some theory explaining why we see this, like why 3 when alpha is 0.5, and why do we, as L grows and C grows, why do we converge to that? And when C is equal to 1, it looks different than the other C's, right? So if you look at the top row, we're getting to something like 2.7 something, whereas when C is 2 and 4, it seems that we're going towards 3. We have some theory to explain why this happens. Essentially, it turns out that it is important to have singletons. So when C is equal to 1, it's possible to have facets that just contain one node. And that distinguishes simplicial complexes from their hypergraph counterpart. It turns out that that's important. Other things we did was a lot of experiments on different empirical studies. What happens to distances in the skeleton graph? Like if we go back to graphs, what happens to distances? What happens to clustering coefficients? What can we say about the assortativity of the networks? We did all kinds of studies on that, which I cannot talk about now. We also looked at criticalities. People like that with percolation stuff. When do we have a giant component? At what value of alpha will I expect to have an infinite component? And we also studied that for the special case of L equals 1. And we did a bunch of other things. And so that was a few years back, but there's no time, of course, to go over that. I just wanted to highlight the main ideas of why we get power law and a mechanism that seems to be natural enough that will produce that, and without explicitly worrying too much about individual nodes and their degrees. So that's all. And I'm happy to answer any questions.
wondering, I'm not from like network science, but like, say you have some actual real world thing, and then you have your model. Okay, so beyond saying they both have a power law, like, are there some, what else can you look at in the real world one and in the model to see whether it's a good model?
That's
What should they agree
right.
on other than just
Exactly. Good question. That's included in what I mentioned towards the end, that we looked at more quantities in the network.
and you just compute?
You can you can vary your so what are the parameters that we can play with here? We can play with alpha, L, and C. We don't have more. These are the only parameters. And then the question is, can you play with these parameters and create realistic networks? And in different scenarios or different fields, network look different, even though they have power law. They look different in some other aspects. So we tried that, and we found that, yes, we can change these parameters to produce different kinds of networks. So other aspects that networks can exhibit, distances. What are average distances, for example? So we show some studies. We can produce networks that are known to exhibit certain properties of those average distances. Another property is called assortativity, and another quantity is like clustering coefficient. Other quantities have to do with topological analysis. Something called my student did is called the Q analysis, which I don't fully remember now, but literature in simplicial complexes look at this, a lot, topological analysis. So we did all these studies, and we found that we can produce different kinds of networks based on these parameters, based on these properties, by playing with the parameters. Of course, there are also other networks that we cannot produce. For instance, our generating algorithm can only produce powers that are greater than 2, because it's 1 + 1 over alpha, right? And alpha is less than 1, so this power is always greater than 2. We know when the power is greater than 2, that's when you have finite expectation in terms of the degree. But there are networks that have powers less than 2, and they have infinite expectation in their degree. We cannot produce those. We can, if we want, by changing our requirement on C, because C is an integer that is positive, so 1, 2, 3, etc. What happens if we make it 0? Which means there's a possibility of sampling facets and nodes from them, creating a new facet without adding anything new. That creates dense networks where the number of nodes does not increase, but you have more facets or more hyperedges or whatever. And so we cannot produce dense networks with this model, but if we allow C to be 0, which is something we wanted to study, but we didn't have enough time to do it, we can create dense networks with C equals 0. I mean, we tried experimenting, but we didn't study theoretically. So those networks, with some variation to our procedure, we can create them as well, but we didn't actually study them. And there is work in literature about creating dense networks. And so the point is, yes, we can create several types of networks with different properties, but not all of them. But I mean, who does, right? So, I mean, it's very tricky to claim something like, I can recreate any scenario. But that's important because people would like to create synthetic networks to work with. Is this a good tool to create synthetic networks? Yes, in general, but there will be scenarios where this is not going to be useful for some fields of studies, I would say. Yes.
So have you thought about about doing centrality measures for hypergraphs? You said assortativity and clustering coefficients. What about centrality measures? Like for graphs, you have degree, betweenness, closeness, eigenvector.
We didn't. So to be honest, we didn't look at that. I had a plan to take this further, but my student graduated, and when he did, I wrote down, all the directions I could go from here. But unfortunately, I didn't find someone who is as good as he was, theoretically and in practice. I mean, he could code anything, and he could analyze anything. And I also did not have, I wasn't able to renew my grant. So this line of research, for me, it kind of stopped. But I still have ideas that I want to explore. If you're interested, we can look at that. I have a GitHub for the product, for the tools that he developed. I think they are all written in a functional language, which is, nice mathematically, but not nice to, port to something else. But so we could work on, future directions. But the short answer is that I didn't look at any of, these things that you mentioned. Yeah. Yes.
I find it interesting that at the graph level, you can not get a power law, then you get a power law when you go to the hypergraph level.
Yes.
But it must depend on how you choose a hypergraph. For example, you can be cheap and just make each edge your hyper edge. Then you're not going to get it's the same.
Exactly.
So somehow you have, I guess, do you have a theoretical result like, you have the underlying graph, no power law, but you choose the right hypergraph, you always get it or often get it or something like that?
That's a very good question. We didn't look at it this way. So let me maybe frame it nicely. So what you're saying is that given a graph, can you define a hypergraph that exhibits okay. We didn't go in that direction, but we thought about what is the natural hypergraph that resulted in this graph. So for example, for the friendship network with the Facebook, right? The graph that we're looking at, the end result is that two people are friends, there's an edge. But that did not possibly come this way, even though you choose your friends, right? So you send a friend request, so you're sending an edge. But the reason why this edge emerged is because somehow you got to know about some group, or you're seeing some news or something, right? So even though you're explicitly creating this edge, the reason why it was created is because there was some kind of an interest that showed you this person. So there is a hyper edge somehow. So we thought about a natural way to rewind from this graph is to take the cliques. That's one example. In the authorship network, we thought that a natural way is to look at the papers, right? So again, because there are so many ways you could end up with the graph, but this graph is just somehow a backbone for something else, right? What is it? We don't know. So going back is not easy. So we looked at the natural way to consider these higher order structures. I mean, the graph is pairwise. You lose a lot of information when you go pairwise. But we chose the natural. I think we chose the natural way, and those are specific to the examples. But in general, that would be an interesting question. You have a graph, define a hypergraph on top of it that exhibits this relation. We didn't look at that. And that's why our procedure, I mean, we wanted to know, right? What is the underlying mechanism? What underlying mechanism can produce these graphs? And so we thought about a general procedure where I have to be driven not by edges or by the nodes themselves. I have to be driven by these affiliations. And this is how we add a paper. right? I must have read some papers. From these papers, I must have identified some authors. And I got in touch with these authors based on my ideas. We collaborated, we created a new paper, right? So this fits exactly the model where we sample edges or facets or whatever, we sample affiliations, and then we pick nodes from these, we create a new affiliation involving the nodes and an additional author or person or multiple. So part of our goal was to actually figure out an underlying preferential attachment mechanism that can result in these graphs. And then, of course, once you have your hypergraph or your simplicial complex, you can create the underlying graph, which will exhibit some weird degree distribution, not necessarily power law, but so going backwards is interesting, but we never really explored it, except in case by case, where we went to the what we thought is a natural way. Yes.
That's a great idea, by the way.
Going backwards? Yes.
No,
It's,
what you
Yes.
said, but also your idea that you take the papers into consideration as you build your network of.
so that was an example that we started with, right? And we thought in general. So if you look at the procedure where you sample affiliations, this is how you start. It's kind of motivated by maybe by the paper example, but we thought it's general enough in any setting where you're sampling groups somehow. You don't know the individual people, right? You sample groups, you hear about some group of people doing something and you got interested. So you sample groups and then you get to know people in these groups somehow, or you identify some of them, and then you try to somehow join them, and then you create other groups. So we thought this is natural way to do it, but of course there are other ways. I mean, that's just what we thought about. So our goal at some point was to find an underlying process that could result in these things. That could be, it's not necessarily true. It could be the explanation of why the power law at these hypergraph levels occur. Yes.
Any other questions? Should we thank the speaker?
Thank you.
And let's thank all the speakers. That's it.
Thank you.
Yeah, thank you.